electron to the right hand side. So when we add 1 electron to the right hand side, then we have overall plus 2 plus 2. Now, it is noticed that the number of electron, the number of moles of electron here is 5, and the number of moles of electron here is 1. And mind you, you must make sure that electron does not remain in the final reaction. That means, what am I saying in a nutshell? That means electron must be eliminated. If this is equation 1 and this is equation 2, since electron must be eliminated, that means we are going to multiply equation 1 by 1 and equation 2 by 5. When we do that, 1 times this, you have this, plus 5 electron to give Mn2 plus 4 waters. Then when we multiply equation 2, now from what we have here, we have MnO4 minus plus 8 protons plus 5 electrons to give you Mn2 plus 4 waters. Now, if we are multiplying equation 2 by 5, that means the ion here, ion 2 here will be 5 ion 2. Then, to give you, so 5 ion 2 plus going to 5 ion 3 plus times plus 5 electron. With respect to this equation, the number of, while we added 5 electron to the left hand side of the equation, is because on the left hand side we have plus 7 charge, and on the right hand side we have plus 2. This one, plus 7, is higher than plus 2 charge. So in order to balance for this plus 2 charge, we need to add electron to the left hand side of the equation. And because electron comes with a negatively charged, so it will reduce this to plus 2 charge. So mind you, you must always make sure that electron is added to the oxidation number that is higher. And in this respect, oxidation number on the left hand side is higher than that of the right hand side. That is for the first equation. For the second equation, it is also noticed that you have plus 2 charge on the left hand side and plus 3 charge on the right hand side. Now, since electron must not remain in the final reaction, we have to remove or eliminate the electron. And since electron is on the left hand side of the reaction in 1, it must be in the opposite direction for the reaction 2, that is on the right hand side. Why are we doing this? Simply because our interest is to make sure that electron does not form part of the final reaction. And in order to do that, it must be eliminated. And for it to be eliminated, it must be in opposite sides of the 2 reactions. That is why in the first reaction, it is on the left hand side, while the second reaction, it is on the right hand side. So in that situation, you have this. So you can rule a line this way, such that you eliminate. And it is noticed now that we have 5 atoms or 5 moles of electron for the first reaction on the left hand side, 5 moles of electron for the second reaction on the right hand side. This can be eliminated easily. Then in that respect, then we write the final product. Here you have MnO4 minus plus H plus, then plus 5 Fe2 plus. These are all what we have on the left hand side. Then followed by the arrow, the Mn2 plus plus 5 Fe3 plus plus 4 waters. This is the final reaction. But in order to convince ourselves that this is correct, then we have to check the number of charges and the number of atoms on both sides of the reaction. And in order to do that, if you want to balance atomically, you have 1 atom of manganese here, 1 atom of manganese here. You have 8 protons here. 4 times 2, that is also 8 protons of hydrogen. Then we have 4 atoms of oxygen on the left hand side. We also have 4 times 0, 4 times oxygen here, 4 atoms of oxygen here. We have 5 moles of ion 2 plus here. We also have 5 moles of ion 3 plus here. So with what I have been able to detail, it is justified that this particular reaction is balanced atomically. So let's check the electrically. Here you have -1 for this molecule. This one you have +8 for this, then you have +10 for this. On this side, +2 for this and +15 for this. This one is not carrying any charge because it is a compound. A compound has 0 charge, so that is why this one is not carrying any charge. Now here, -1 plus 8, that's +7. +7 plus 10 plus 17. You have +17 for the overall charge on the left hand side of the equation. Here too, you also have +17 as the overall charge on the right hand side of the equation. Therefore, this reaction is a balanced redox reaction. Questions designed for oxidation and reduction. Question number 1. Reaction of sulfur 4 oxide with oxygen to give sulfur 6 oxide in the presence of vanadium 5 oxide is an example of A. Homogeneous catalysis, B. Heterogeneous catalysis, C. Inert catalysis, D. Contact catalysis. 2. The oxidation number of hydrogen changes in the reaction between 2 moles of hydrogen and 1 mole of oxygen to produce 2 moles of water from A +2 to +1, B 0 to +2, C +1 to +2, D 0 to +1. Question number 3. The oxidation state of sulfur in tetrasulfate 6 acid is A +5, B +6, C +4, D +2. Then number 4, differentiate between oxidation and reduction. Answers. Question number 1. It is evident that SO2 to oxygen, reacting with oxygen to give you SO3, a reversible reaction in the presence of vanadium 5 oxide, and this is a balanced reaction for that process. So here, homogeneous catalysis. When they say homogeneous catalysis, it means the interplay between the same molecules, in the sense that you started with sulfur 4 oxide and you are ending at sulfur 6 oxide. They are of the same system, so it is homogeneous. This is homogeneous. Now B, heterogeneous. This is not heterogeneous because the parent element here is sulfur, and in the product is also sulfur. So if it is heterogeneous, automatically the parent element will change, and since the parent elements remain the same, it is not heterogeneous. In that regard, A is the answer to question number 1 because of the fact that it is homogeneous catalysis, in the sense that the parent elements in both reactant and product are the same. Question number 2. The oxidation number of hydrogen changes in the reaction between 2 moles of hydrogen. This is hydrogen gas, 2 moles of it to give plus a mole of oxygen gas to give water. So in this regard, we are asked to calculate the oxidation number of hydrogen from at this state to this state. At this state, since this is a gas, the oxidation number here is 0. Here it is a compound which can